Hey guys, Mr. Wood back and for another lesson, and we are off into chapter 5. And so, as always, we have got to start with jokes. It's downhill from there. Okay, why did the robber wear blue gloves? Did you know the robber wore blue gloves? Because they didn't want to get caught red-handed. And why was the scientist head wet? Because he had a brainstorm. Okay, today, again, guys, remember next week and whenever you watch this, because we're moving into chapter 5. And like I said, if you don't watch this until out during fall break, that is fine. But we're going to keep moving. We got to keep moving. And so remember, again, I got it right here on the board. So on Monday, Tuesday, the quiz chapter 4 is due. We do the first, actually a little more than half of the test. And then on Wednesday, Thursday, we finish the test. The redox titration lab is due, and we're going to move well into chapter 5. So when we get back from break, we're going to be, again, well into chapter 5. And it won't be the first week we get back from fall break, but after that, we will have our chapter 5 test. And we're now not going to be covering nearly as much ground. So here we go, into chapter 5. So here are the problems. So not nearly as daunting as it used to be, or as it was prior to this, but here are the problems. And again, we're going to have a test just on 5. I'm going to look at it and see if it'll be a 1 or 2 day test just for the sake of time. I'm really going to maybe try and make it be a 1 day test. And we'll do the same with chapter 6. Sorry, I just am checking my text messages there. My wife is recovering from that appendicitis attack. She's doing well, though. She's doing good. But okay, so there are the problems for you guys. This chapter is on gases. And if I was standing in front of you guys right now, I would say, okay, what do you remember about gases? And hopefully there are some things you guys could remember. Some of the gas laws, Pivner, which we're going to look at a little bit today, and we're going to get into this chapter. This is definitely still going to be a good amount of review going forward. But relatively few substances at room temperature are gases. Ionic substances are never gases. That's because they have strong bonds. So if we have a metal connected to a non-metal, like NaCl or MgBr2, those are not going to be gases. Some molecular substances are gases. Some have weak bonds. And your guys are not going to be able to see it. I'll move the camera over here. Let me, just on our periodic table on the wall here. But just to note, so on our periodic table on the wall here, so elements that are in red, so up there, especially on the upper, the right, far right-hand section of the periodic table, those are gases. So elements in red are gases. Elements in black are solids at room temperature. Blue, it's kind of hard to see it, but number 35, bromine, and number 80, mercury, those are gases. And then elements that are in gray, and again, it's kind of hard to see, those are synthetically made. But the point of this chapter is gases. And so gases are the elements on our periodic table that are in red, and which, again, there's not very many that are in red on the periodic table. Okay, so gases. A gas is a substance above its boiling point. Vapors are substances below its boiling point that has evaporated. And to be honest with you, I'm not going to be, I'll probably use the terms interchangeably incorrectly there some of the time. But okay, and then what's on the right is just the air, the composition of the air. And you can see that the mole fraction, which is really the percent, is that most of air is nitrogen, N2, and then oxygen, and you can see the others are a very small component. So real quick, just kind of a diagram going back to just showing diagrams. So again, if we have an ionic substance, so if we have something like this, CaCl2, this is not going to be a gas because it's an ionic compound. But an example is O2. Okay, so what happens in O2, if I go back to the dot structure, oops, so I have a bond here and here. So I have a double bond. But since oxygen connected to oxygen, whenever something's connected to itself, the electronegativity difference is always going to be 0. So it's going to be non-polar lemons. So if I have oxygen like this, and then I have another oxygen that comes up to it like this, this bond here is a really weak bond. It's LDF, and we're going to talk about this later in the class. London dispersion forces. When it's a gas, this bond can be easily broken. It can be easily broken. It's not held together very strong. It's easily broken. Up here in CaCl2, when it's an ionic compound, it's held together real strong, and so it won't be broken, so it'll be a solid. Okay, so a little bit on the molecular level, what is going on with gases. Okay, and then the composition of air. Behavior of gases, oxygen at room temperature travels, get this, about 1,000 miles an hour, so it's moving really fast. It collides 2 to 5 billion collisions per second. That's almost hard to imagine. It's moving so fast. And it's mostly empty space. So that's a kind of an illustration there, or the numbers. You can see that as a gas, it has about 1,000 times the volume as it does versus a solid, which means then that it's very compressible. So I brought out my plunger here and I'll get it out. So gases are very compressible. Oops. So this nothing very exciting to see, but here, so if I close this, but because there's air in there, a gas, I can compress it. I can compress it down. I can't get it all the way in, but I can get it. I can compress it down. With a solid and a liquid, I cannot do that because their molecules are much closer together. Let's see here. Okay, and then this is showing, and actually what I have done in the past is I have done a pop can where I take a pop can and an open, empty pop can, and I invert it into a beaker of cold water, and it crushes the can. And the reason it does that is because it's because of the pressure on the outside of the can. Sorry guys, I'm bogging down here because I want to make sure that we're seeing this. But so gases are compressible. They have a lot of space between the molecules. I always do this analogy. But if we compared a solid, a liquid, a gas, think about going driving, and say you like to snowboard and you are coming home from a weekend or Sunday snowboarding up at Copper Mountain, and when you come home, it's a traffic jam, and you can barely move, and that's where the cars are packed tightly together and they can barely move. Well, that's like a solid. Well, a liquid would be like being out here on 470 at about 5 or 6 o'clock at night. And again, the cars are pretty tightly packed, but there's more spacing and there's more movement. So a solid and a liquid are pretty close to the same, but a solid is more compressed, not as much movement, where a liquid is a little bit more spacing, a little bit more movement. A gas is always, it's like driving in the wide open. And I always think of driving through Wyoming. Well, you can drive sometimes for 5 or 10 minutes and not even see another car. Well, that's the way it is in a gas. So, okay, well, one thing with gas is pressure. And on the formula sheet, this is actually something that's not going to end up being on, or no, I'm sorry, it is on the formula sheet. So I'm going to real quick go back to the formula sheet. Okay, so on the formula sheet, the front, and so if we go to the back of the formula sheet, we've got 1 ATM is 760 millimeters of mercury and 760 torr. So that's what, if that's on that, they're going to expect you guys to not have to remember that. And so I kind of don't think the kilopascals will be on the AP test, but it certainly could be on our test. So gas pressure is a pressure caused by collisions, and it's measured by a barometer, and you can see mmHg means millimeters of mercury. It's the height of a column of mercury, which is 760 torr, which is the same as 1 atmosphere, and then 101.3 kilopascals. And a matter of fact, it might be worth on our formula sheet writing that in. So what I'm saying is on our formula sheet then, so on our formula sheet on the back, right here where it says right here, so 1 ATM is 760 millimeters of mercury, 760 torr. I would just write in equals 101.3 kilopascals, equals 101.3 kilopascals. So that, again, is, I don't think that'll be on the AP test, but it's certainly a possibility for our test. And that, all this stuff we talked about again in first year chem. Okay, so then back to, I think, a problem that would be an easy problem for you guys to do. So this problem right here. So convert 732 torr to kilopascals. Okay, so again, if we go back to just our rules with conversions, which I think for you guys is something you got a lot of experience of, but if I got 732 torr and I want to go to kilopascals, so there's my setup. So then torr is going to go on the bottom and kilopascals are going to go on top, and the numbers are 760 and then 101.3. And remember, my sig figs are going to be determined by my starting point, not what is in here. And so if I do that, what I get is 97.6. I'm just going to make sure I got it written down in my notes. So I got 732 times 101.3 divided by 760, 97.6. So there you go. Simple little conversion, but we've got to make sure that we are good on the conversions. Okay, so back to chapter 5. And again, like I said, a lot of, it's going to be, again, a lot of review. Okay, so we've done this page. Okay, the next page I'm actually going to skip. Here we're going to talk about Boyle's law, but here's just, again, one of those for your information things. Blood pressure is the force within arteries that drives the circulation of blood. It's like water pressure in a plumbing system. When the heart contracts, the blood pressure increases. Between contractions, blood pressure decreases. The systolic reading is the peak during a contraction. Diastolic is the lowest. Taking blood pressure, you put your hand in a cuff. And I think they usually like the readings to be the higher number in the 120s and the lower number in the 80s or below. So anyway, something about pressure. Okay, the first chemist was kind of a famous chemist, was a guy named Robert Boyle. On this page, there's nothing you need to write down here, but he, and at the time when he was doing this, there was alchemists and they were trying to turn metals into gold, but he studied gases and he noticed a relationship between pressure and volume. So that's all you need to know there. And then if we continue on, he noticed, like I was talking about, that if the pressure increases, the volume decreases. So if I go back to my plunger thing, which I don't know what it is, here it is. So if I again go back to the plunger, what he discovered, what Boyle discovered, was real simple. So when I increase the pressure, when I put pressure on this, the volume goes down. So he had a simple relationship, an opposite relationship that he noticed. Pressure goes up, volume goes down, is what Boyle noticed. Okay, and then it actually ends up becoming mathematical. What did I do with my notes? Sorry, guys. Okay, so here we are. Okay, so that's what he knows. Pressure goes up, volume goes down. And then from that, we get gas law number one, which is not on the formula sheet, but over there, just like it says, volume, that kind of weird symbol, looks like the alpha symbol kind of. Volume is proportional to 1 over P, but pressure times volume equals K, a constant, or pressure P1 times V1 equals P2 times V2. Okay, so let me just write this on the board. This is not on the formula sheet. Okay, so what this is just saying, and again, all this is review, but what we're saying here is that the volume is directly proportional to 1 over P. So Boyle's law is simply put as pressure times volume equals K. K is a constant. And so what we can say is P1 times V1 equals P2 times V2. Okay, so that's Boyle's law. You'll never need to know the name of that, but understanding that, and what this really says is if the pressure goes up, the volume goes down. Those are indirectly related. They're oppositely related. One goes up, the other goes down. Okay, so then we will do a simple little gas law problem here. Okay, so here is a simple little gas law problem. So 946 mils of gas at 726 torr. As the pressure exerted on it changed to 4,460 torr, calculate the new volume. So what I have, Ethan, I'm just in the middle of are you done?
I forgot to tell my
Oh, okay. Thanks, brother.
Yeah.
Have a good weekend, man.
Yep, thank you.
Okay, so if I go back and do this problem, again, in first year chem, what I always did is I always make sure that the students, and I would do this in our class too, is I would label everything. I would tag everything. And on this problem, obviously, it's a problem. We did problems like this in first year chem, but it says, so if I label, so I have a volume of 946 mils, and I have a pressure of 726 torr. And then it says the pressure exerted, so here's a second pressure, is 4,460. And then what is the new volume? And so I always label everything. I make sure that the units are right. One thing in first year chem that you always had to make sure of is that the units agreed, which they do here. And then I always had to make a prediction. And so here, if the pressure is increasing, I would expect the volume to go down. So just my qualitative prediction would be the volume would go down. Okay, and so then I do the numbers. So I have P1 times V1 equals P2 times V2. So if I plug everything in here, make sure you guys can see this. So I have 726 torr. I have 946 mils. And again, the units are always kind of a guide to me. So then I have 4,460 torr. And then this is X. So if I solve for X, so I'm going to isolate X all by itself on one side of the equation. And again, if I always know units tell me if I'm on the right track. That would leave me in milliliters. And so what I get here for volume for V2, I get 154 mils. And always make sure doing these AP problems that you you watch your sig figs and you label. And I go back in first year chem, and then I go back and say, okay, well, we said the volume would go down. Well, sure enough, the volume went down, so I'm probably on the right track. Okay. Okay, I want to do maybe one more problem. Okay, so here is another problem that is this is another ideal, or not an ideal gas problem. This is another Boyle's law problem. So again, I'm going to label everything. The question here is different. This one is different than what we had in first year chem. This one is asking about, does this obey Boyle's law? So I'm going to stop there. Okay, so remember, okay, so I'm going to be writing here. So for Boyle's law, we know that Boyle's law that pressure times volume equals a constant. Pressure times volume equals a constant. Well, again, if I label everything, so we have a pressure of 0.1300 atms. We have a volume of 172.1 mils. It says the pressure is increased to 1 atmosphere. Okay, so here's a second pressure. It's 1 atmosphere. And this time they give us the second volume. The second volume is 22.08 milliliters. Okay, so I'm going to go back and I'm going to do this for both of these. So for scenario 1 and scenario 2, so if I have 0.1300 times 172.1, so this times this, that gives me 22.37, I think. So 0.1300 times 172.1 gives me 22.37. Now I'm going to do that for scenario 2. So again, I'm going to take 1 times 22.08. Now I'm going to compare those two. The question was, does this obey Boyle's law? Well, does pressure times volume equal a constant? Well, not quite. And so the answer here is no, it does not. This does not obey Boyle's law. It's really close to it, but it doesn't. And this is something we're going to talk about later in the chapter. We're going to talk about ideal gases. Well, this is ammonia. And ammonia, again, going back to doing dot structures, ammonia is a very polar molecule. So we get a negative and a positive. Well, if I have another ammonia here, like this, and so again, I have a negative and a positive. You guys can't see that. Negative and a positive. Well, this, because this, as a matter of fact, this is a hydrogen bond. This is something we're going to talk about later on. And in this chapter, I'm just going to say, okay, these are ones to watch. Water would be another one. Because this is such a strong bond right here, it's going to be hard to break it. And because of that, that's why this does not obey Boyle's law. But the answer to the question is does not obey Boyle's law. That is a good place to stop. Guys, get yourself ready for the test. Like I said, if you guys have any questions, you want to do a quick Google Meet, just let me know. Friday I can't, but next week I can. And hey, study hard, and I will see you guys next week.